Swayam Prabha. Digital India. Educated India.
So, welcome back. So, we have been looking at this rule based production systems, and we have seen in considerable detail the idea of matching of rules with data. Rules have patterns, patterns may have variables, patterns may have Boolean tests, and data will have the data that these patterns must match, and that is what is done by a match algorithm. What is the output of the match algorithm? It takes all the rules, matches it with all the data, and gives you what is called as a conflict set. So, what is a conflict set? Let us look at this small example here. The two rules that we spoke about. The first rule is for sorting, we call it swap sort. It simply says that if there are two elements which are out of place, that then we do not, as far as the conflict set is concerned, actions do not concern us, because we are simply trying to find out which rules are matching. But we know, of course, that the actions were that we had to modify those two records essentially. If there is a record with value I and index I and value x, and there is a later record with value less than x, then interchange the values of the two records. Likewise, we have seen the ranking rule. It says that if the next rank is R and there is a student S with marks M who has no rank assigned, and there is no student with higher rank, then assign the rank and increment the rank to next rank to this thing. Let us say we have some working memory elements. We have got some 4 array elements here, and we have some 4 students here with marks. One student has already been assigned the rank 1, and you will notice that the next rank is now 2 essentially. What is the conflict set? The conflict set, let us say these are the only 2 rules in our system and this is the only data. The conflict set says which instances of these rules are matching and with what data essentially. So, let us look at that. The first rule will match anything, right. The first pattern of the first rule will match anything. It simply says there is an index I, it has a value x. We have not stated what is I, we have not stated what is x, we have simply stated that there is an index I and there is a value x stored in that. So, obviously, it will match all the 4 elements, but we are interested in those matches which contribute to a rule matching, which means that the second element also must match essentially. So, what is the second element here? It says that there is an index j which is greater than index I, and it has a value y which is less than the value x. So, as you can see from these dashed lines, this rule will match the first element and the third element essentially. Why the first and the third element? The first element has index 1 and value 7, the third element has index 3 and a value 3 which is less than 7. So, that is why it matches that. So, this rule says that okay, I have spotted 2 elements out of place, we can go ahead and swap them essentially, but there are other rules which are also waiting, and that is why we have a conflict between them, right, and that is why we have a conflict set. Let us look at another example here. Again, the next rank R will match this all the time, and there are in fact, as you can see, there are 2 students here, Eva and Anil. Both have got 79 marks, both of them do not have a rank assigned. There is a student with higher marks 89, but the student already has a rank. Remember that this negative pattern said that the student must not have been assigned a rank. So, we can ignore Rashmi here, she has already got rank 1, and now there are 2 students Eva and Anil both are candidates for the next rank, which is 2 essentially. What we have shown here is only these 2 lines, which says that this rule matches 5 and 7, which means that this rule says give Eva the rank 2. Of course, there will be another instance of the rule which will say give Anil the rank 2. So, if you draw the conflict set, if you look at the conflict set, then these 2 rules that we have shown, I have shown here in red. There are 3 instances of swap sort which are ready to swap elements, 1 and 3, which means 7 and 3 are out of place. So, the second rule says 2 and 3, which says that 9 and 3 are out of place, and the third one says 2 and 4, which says that 9 and 8 are out of place. So, there are 3 instances of rules which are ready to fire, and they all 3 go into the conflict set. Likewise, there are 2 instances of ranking rule. We already observed this, that both Eva and Anil can get rank 2, and so therefore, we have these 2 elements in the rule, and that is what is called as a conflict set. So, a conflict set is a set, each element is a tuple made up of a rule name and the timestamps of the data with which it is matching. So, we will access working memory elements by their timestamps essentially. So, as you can see 1 and 3, 2 and 3, 2 and 4 for the swap sort this thing, or 5 and 7, 5 and 8 for the ranking rule essentially. This is the conflict set. So, you can see that the task of match is to basically construct this conflict set. It look at all the rules, look at all the data and come up with this set, out of which one would be selected. That is called conflict resolution, as seen on the right hand side of the diagram. Once you have the conflict set, you give it to some resolve component, and that will pick one rule with one data. And we have already said that that is the key to problem solving, which rule to pick next. This is the same swap sort rule that we have been talking about. It basically spots 2 values which are out of place and says that it is time to swap them or something like that. Now, if there is a large set of working memory elements, in the example we saw there were only 4, out of which there were 3 which were ready to be swapped. The rule may match many pairs of the elements. And as we have said, a set of that kind of matching rules with their data is called the conflict set. And the inference engine selects one rule from the conflict set and says, okay, fire that rule or execute that rule. This is the term we use, either fire or execute. But you can give some thought to this matter. What would happen if you allowed multiple instances of rule to fire at the same time? What is the kind of difficulty we may face? Are there some problems which can be solved by parallel execution of rules, or will that kind of some conflicting situations in some other situations? We will not go in too much into that, but you can give some thought to that. We want to focus instead on conflict resolution, which is choosing which rule to execute next or fire next essentially. So, conflict resolution asks this question, which rule to pick essentially. Let us look at that. As I said, people who implement the rule based systems for us to use, or if you want to say people like us who implement rule based systems for some user to use, have to offer a set of strategies which the user can select from. What are the different strategies that one should consider? Let us quickly go over them, and we will later go in more detail as to how to implement them. As we said, the key to effective problem solving is to make informed choices. In heuristic search, we try to use a heuristic function to help us decide which move to select next. But we also said that the heuristic function should be given to us by the user. At least in this course, that is what we have said. I must have mentioned during the planning lectures that the community has tried to evolve domain independent heuristics in the planning task, which says basically that somehow if you can look at the problem and get a rough idea of which move will take shorter amount of time, a rough idea, not necessarily correct, then we can use that as a domain independent heuristic. And the way that the planning community does that is by solving what is called as a relaxed version of a planning problem, in which you relax the conditions when an operator applies and then use that to solve the problem. And typically those relaxed problems can be solved in polynomial time, so that even though the search space is exponential, the heuristic function is useful to have. Such a heuristic function is useful to have. Anyway, we will not get back into that. In rule based systems, the rules encapsulate such knowledge gleaned from human experts. Somehow we have said that that of all the things that you can do, the expert tells us as to what are the things that can be done essentially. The problem that we are now facing in conflict resolution is that when more than one rule matches data, the inference engine has to make the choice of which rule instance to execute essentially. This is somewhat analogous to in heuristic search, which element to inspect next essentially. So, we look at various conflict resolution strategies now. The first strategy is called refractoriness. It says that a rule instance may fire only once with a set of matching working memory elements. This would be particularly relevant if the selected rule instance does not modify the working memory that was matching its preconditions. If it does not modify them, it will match again in the next cycle. So, we do not want to keep firing the same rule again and again and again. So, this is a strategy which says that each rule with a given set of data, and remember that the data is identified by their timestamps. Each rule with a given set of data will fire only once and not more than once, and that strategy is called refractoriness. It is a key part of all systems that we want to implement. The idea comes from the way neurons fire in animal brains. The way neurons fire is that they receive excitation from other neurons, and when there is enough excitation built up, enough potential built up and goes beyond the threshold, then they fire in turn and let loose a stream of pulses down its axon essentially. So, once it fires, the excitation is kind of finished and it does not fire again essentially, and that is what is called refractoriness. The idea that we are using in rule based systems is similar in nature, also as we will see implemented in a very similar fashion. Just a word from the Merriam-Webster dictionary. The insensitivity to further immediate stimulation that develops in irritable and especially nervous tissue as a result of intense prolonged stimulation. So, you keep giving the same stimulus, do not expect the system to keep responding at the same pace essentially. As we will see, this happens naturally in an algorithm that we will study called the Rete algorithm or the REAT algorithm as some people call it. The next strategy we can talk about is lexical order. This says that of all the rules that have matching instances, choose the first one that the user has stated. So, presumably the user, you can imagine a user sitting with a paper and pencil and writing down all the rules. Take them in the lexical order in which the user has written the rules. So, clearly you can see that the onus is shifting to the user here. If a rule has multiple instances which different data, so we have seen that in swap, sort or ranking, this thing, that a rule may have multiple instances which are fired. Lexical strategy says choose the instance that matches the earlier data, the data that was first presented. Okay, and we can do this by looking at the timestamp essentially. You can see that the strategy places the onus of this choice on the user. The user is more like a programmer essentially. We will see next week sometime is that this strategy is used in the programming language Prolog, which is why it is more of a programming language and less of an expert systems shell that OPS5 is considered to be, because in OPS5 this constraint on the user is not there to write the rules in a particular order which would make it more efficient or which should make even work essentially. You can write programs in Prolog, if you change the order then it will just simply go into an infinite loop. So, Prolog in that sense deviates from the idea of pure declarative programming. So, in fact some people differentiate between pure logic programming and actual logic programming, which is like Prolog essentially. In pure logic programming you would only state the rules, and if the solution was a consequence of the rules it would be found, but in practice in Prolog you have to state the rules in a careful order. Coming to OPS5, OPS5 has two very interesting conflict resolution strategies. One of them is called specificity. This says that of all the rules that have matching instances, choose the instance of rule that is most specific essentially. And you should think about this, and it is a very insightful idea, is that of the many things that you can do, the most specific one or the one which matches the most specific conditions, we are talking about the left hand side, we are not talking about the right hand side. The right hand side may have any number of actions, we do not care. The conflict resolution strategy does not look at the right hand side, it simply says that these are the matching rules and these are the working memory elements that you are matching, and that is the conflict set. It does not look at the right hand side at all. So, when you say most specific, we mean the most specific left hand side essentially. So, the left hand side which has the most amount of conditions is probably the best rule to fire, and that is what this strategy of specificity says. And it can be measured in the number of tests that patterns in the rules need essentially. So, if there are many patterns with many tests, then it is more specific than a rule which has fewer patterns and fewer tests. This strategy says if there are two such rules which are candidates in the conflict set, choose the one which is more specific, which has more tests essentially. The intuition is that the more specific the conditions of a rule are, the more appropriate the rule is likely to be in a given situation. Remember that the working memory models the short term memory of the problem solver. So, everything that the problem solver knows about the problem, the data that it has acquired is there in the working memory. If there are rules which are looking at more of the data, they are likely to be more specific and perhaps, according to this strategy, more relevant essentially. Rules only consider the problem solving knowledge, and they reside in the quasi-static long-term memory. So, when I say quasi-static, I mean it is almost static, that most implementations you input the rules and forget about it, and then just keep using it to solve different instances of problems. So, rules do not change, but what this strategy is saying is that more specific rules are better than less specific rules, or more specific rules are better than more general rules. This takes us to this idea of default reasoning. So, we are making small forays into reasoning. It is not really the main thrust of this course, and we have already reached the 10th week. So, we are coming towards the end of the course. But as I said, all these things are tied up together with one with the other. So, let us look at this idea of default reasoning very briefly from a domain which is a favorite of mine, and that is from the game of contract bridge, which I will highly recommend all of you to look at. It is something which will be with you the rest of your life once you have gotten into it. Anyway, so here is an example from bridge bidding. So, the game has two parts. We did mention it during game playing, right. One is the first part is the auction, where you bid for a contract, and the second part is the actual playing out or trying to fulfill the contract. So, we are talking about bidding here, and we are talking about default rules. So, if you want to write a rule based system, you must implement it in such a way that it is complete, which means that in any situation it tells you what to do. The idea of default reasoning is that if you can't think of anything very specific, there must be some very general rules or default rules which will tell you that you can always do this thing essentially. So, the system should never get stuck essentially. So, that is easy to implement in bidding here. There is a default action which says pass, do not make a bid, or do not enter into the auction essentially. And if we call this a pass rule, it simply says that if turn to bid of player X, and so just ignore the second pattern here for the moment. The first pattern simply says if it is your turn to bid, then make a pass bid. Okay. If you do not know anything else, just say pass. Pass basically means that I am not making a bid for the contract essentially. The second pattern is more to do with implementing the game of the bridge so, as you probably remember from the games lectures, it is a game played between 4 people. So, you can see that there are 4 players. Typically, we call them north, east, south, west, and bidding goes or play also goes in this direction. And the second pattern here in this rule, it says next after X is Y. So, if X is playing, then after that Y will play. So, what is this? This means that in your knowledge base or database there would be 4 records, and they would say after north east plays, after east south plays, after south west plays, and after west north plays. So, that is simply to take care of the implementing the game, and essentially this says that if X has made a move which is to bid pass here, then the next player to bid is Y, and because that is what the record is saying, that after X it is Y. So, for example, after north it is east. The important part is that we are talking about a default action, that if you have nothing, no reason to bid something else, just pass, and I have friends whose status on their social media site says pass is also a bid, because there are people who do not know when to stop. Here is just one rule which is more specific than the pass rule, and you do not want to get into the game here, but essentially there is something called you measure high card points in a game, and you look at the shape of the hand, how many hearts you have, how many spades you have, and things like that. So, if you have 15 to 17 high card points and if your shape is balanced, then bid 1 no trump, if nobody else has bid anything. So, this is what is sometimes called as an opening bid essentially. If nobody else has bid anything, and if you have this pattern, then make this bid of 1 no trump. And as you can see in an OPSFI like language, you can write this as a rule. So, the first pattern is still the same, it is X is player to bid. The second pattern simply says after X, Y will bid. The third pattern says this pattern that we are talking about, that points are in the range 15 to 17. So, the points are either 15 or 16 or 17, and the shape is balanced. Let us assume that the shape is a categorical attribute, and you can have different names for different shapes, and let us stick to some simple thing here. And it says that no other player, no y which is not the same as x, has made a bid in round 1. So, you are the first person to bid, then you can make this bid called no trump 1. So, 1 no trump. The purpose of giving this here is simply to point out the use of specificity as a strategy. If you have two rules which are in contention, choose the rule which has more specific. So, if you have something to bid in the case of bridge, make that bid. If you have nothing to bid, you do not have a pattern which calls for a bid, then pass essentially. So, the rule specificity will make the right bid here. If you had used some other strategy, then who knows, with a good hand also you might pass and we have to look for another partner or something. As a small exercise, write rules about birds essentially. So, you want to be able to say that birds can fly, which is a nice piece of knowledge to have, but sometimes they do not fly. So, if they are penguins they cannot fly, if they are ostriches they cannot fly, if it is emu you cannot fly, or if it is dead it cannot fly, or if it is a caged bird, you must have heard about that in India, then it cannot fly. Try to implement a set of rules which will conclude saying that okay, it is a sparrow and a sparrow is a bird, so it can fly, and things like that essentially. One more strategy that we will look at is called recency. It says there are all the rules that have matching instances, choose that instance that has the most recent working memory element. This is not looking at the rule, this is looking at the data. It is saying that the latest, a rule which matches the latest data is the one that you should select essentially. It can be implemented by looking at the timestamps of the matching working memory elements, and I had mentioned that timestamps will be used in conflict resolution, and this is where they are used here. The intuition is that when a problem solver adds a new element to the working memory, then any rule that matches that working memory element should get priority. Okay. So, the idea is that recency can facilitate what can be thought of as a chain of thought, chain of thinking, that you are making some inferences, you are making some actions and you want to carry forward on that. Recency will take care of that. You added a new element, it triggers a rule, so use that rule to match. We can maintain a priority queue. We will look at the implementation details as we go along essentially. So, our last strategy which has been used in Ops 5, it is called MEA, which stands for mean sense analysis. You may remember this from the lectures we did on Simon and Newell's work. And Ops 5 has a specific way of looking at this strategy, and it is as follows, that the idea is, so you have rules which look at part of the problem and in a pattern directed fashion addresses part of the problem. So, we saw this example where the state had many different patterns and each pattern triggered some rule and so on and so forth essentially. What the mean sense analysis strategy says is that you partition the set of rules on the context and focus on one partition at a time. One can think of each partition as solving a specific sub goal or reducing a specific difference. But remember, we are doing in forward chaining match, forward reasoning fashion, not in backward reasoning fashion that we talked about earlier. But you can implement that aspect by creating these partitions. So, it is like if you are building a house, you have to first make the basement, then you have to make the walls, then you have to make the windows and doors, then the roof and things like that. So, there are things to be done in a particular order, and all the rules, different type of rules that you may use for making the basement will be put into one partition. After you have built the basement, you will worry about the walls and so on. Of course, I am not saying that building a house is so similar, so simple, but you can think of it like that, at least the operational part. The context is set by the first pattern in the rule. So, in this MEA strategy which came with OPS5, the first pattern defined what is the context. All rules in the same partition had the same first pattern. So, you could, when you are writing rules, you could say, okay, these are rules for constructing the floor, these are rules for constructing the house. So, these are patterns which set the context essentially, or constructing the walls and constructing the windows and things like that. What MEA strategy says is that you apply recency to the first pattern in the rule, and if there is a tie, then specificity to the remaining patterns. It is a very interesting strategy, and you should give some thought to what kind of problems this will be useful in essentially. Okay, so we will stop here. We have described the language OPS5. We have talked about it as a programming language. We have talked about it as an expert system shell. We have talked about the inference engine, which said that there is a cycle of match, resolve and execute, and keep doing this till somehow the problem tells you that it has been solved, essentially some termination criteria which will be implemented in some rule which will match at some point of time. But how to do this efficiently? It is a very key question, and we will look at that in the next session. So, see you then.